Have you ever really thought about the speed of chemistry itself? I mean, really? Well, today we're going to dive deep into the world of chemical kinetics and answer that one huge question: how fast does a chemical reaction actually go?
I mean, think about it for a second. A firecracker just bam! It explodes in a flash of light and sound. But then you have an iron nail, right? You leave it outside, and it takes years to slowly, almost invisibly rust away. Now, both of those are chemical reactions, but obviously their speeds are just worlds apart. So, what's controlling the gas pedal here? Well, the answer is in a field called chemical kinetics. This is the part of chemistry that isn't just asking, hey, what's going to happen, but how fast is it going to happen? And the best part? We've actually got this really powerful tool that helps us predict and even control that speed. So let's get into it. We're going to break down the recipe for reaction speed. In chemistry, we call this a rate law. Now, it might look a little intense at first glance, but you'll see it's actually a super logical, kind of beautiful equation. Okay, so here it is. This is the generic rate law, and it's basically our map for the next few minutes. You got the rate itself, this thing called a rate constant, which we call K, the concentrations of our ingredients, A and B, and then these little superscripts, A and B. We're going to go through each piece, one by one, so it all makes sense. First up, let's talk about the rate. This is the easy part, you know? It's literally just how fast the reaction is going. We measure it by watching how quickly the amount of a chemical changes over time, usually in units like molarity per second. Simple as that. Next up, we've got concentration, which you see in those brackets. So for any reaction to actually happen, molecules have to physically bump into each other. Concentration is just a way of saying how crowded they are. It's kind of like a party, right? The more people you cram into a room, the more conversations and interactions you're going to get. Same exact idea with molecule. And now for K, the rate constant. Okay, this little letter is a huge deal. You can think of it like a unique fingerprint for every single chemical reaction out there. It tells you the reaction's own built-in natural speed at a certain temperature, no matter how crowded or not crowded the molecules are. All right, so now we get to what I think is the coolest part of this whole equation. Those little exponents, A and B. We call them orders. And honestly, understanding them is the secret to really getting rate laws. They tell us exactly how much of a difference each ingredient makes. So what is order, really? It's not just some random number we can guess from the main reaction. Nope. It's something we can only figure out by doing experiments. And it shows us this hidden connection between how much stuff you have and how fast things happen. The best way to think about a reactant's order is to see it as its power lever. It tells you exactly how sensitive the reaction speed is to a change in that one ingredient's concentration. So it's not about how much of it there is, but about how much that amount matters. And this slide just shows that difference perfectly. So if a reactant is first order, like you see on the left, you double the concentration, you double the speed. It's a straight one-to-one relationship. But if it's second order, doubling the concentration doesn't just double the rate, it quadruples it. That's a huge difference, all from that one tiny little number. Okay, that's enough theory. Let's see how chemists actually do this in the real world. It's time to put on our virtual lab coats, because we're going to solve for a real rate law using some actual experimental data. It's kind of like being a detective and solving a logic puzzle. So here's our case file. We're looking at the reaction between ammonium and nitrite ions. And over on the right, you see our clues, the results from 3 different experiments. Each row shows us what they started with and the initial speed they measured. Our job? Use this data to figure out the rate law. And the strategy we're going to use is actually pretty simple and, well, really clever. We're going to isolate one suspect at a time. We'll find 2 experiments where only one ingredient's concentration changes, see what that does to the speed, and from that, we'll figure out its order. Then we just do it all over again for the other one. Okay, let's start with the nitrite, the NO2-. Take a look at experiments 1 and 2. See how the concentration of ammonium, NH4+, stays the same? It's 0.100 in both. The only thing we're changing is the nitrite concentration. It doubles from 0.005 to 0.001. So the big question is, what does that do to the rate? Well, look at that. The initial rate also doubles perfectly from 1.35 up to 2.70 times 10 to the -7th. So we doubled the concentration and the rate doubled right along with it. A perfect one-to-one change. That tells us without a doubt that the reaction is first order for nitrite. Easy, right? One down, one to go. Now let's figure out the order for our other reactant, the ammonium, NH4+. This time, let's compare experiments 2 and 3. See how the nitrite concentration is now the one that's being held steady, while the ammonium concentration doubles.
And would you look at the rate? It goes from 2.70 to 5.40 times 10 to the minus 7. It doubles again. So just like before, we double the concentration and the rate doubles in response. This means the reaction is also first order with respect to ammonium. And just like that puzzle solved, we found the order for both of our reactants. We can now write out the complete final rate law for this reaction. The rate equals K times the concentration of ammonium to the first power times the concentration of nitrite to the first power. We did it. So why do we go through all this? Why does any of this matter? Well, because being able to control the speed of reactions is, and I mean this, absolutely fundamental to our modern world. Think about it. Designing a medicine that releases slowly over 12 hours instead of all at once. Or creating catalysts that let us manufacture things faster and stronger. Or even just making sure the airbag in your car inflates in milliseconds, not seconds. It all comes back to mastering these rate laws. So let's just quickly recap the big takeaways here. First, rate laws are the recipes for reaction speed. Second, and this is crucial, you can only find them through experiments. You can't just look at an equation and guess. Third, that little number, the order, is the secret ingredient in the recipe. It tells you how much each thing matters. And finally, knowing all this gives us the power to control the chemical world all around us.
And that kind of leaves us with one last big thought. We've just seen that chemists can figure out the exact recipe for how fast a reaction goes. So if we have that power, the power to control the very pace of chemistry, what amazing new medicines, materials, or technologies do you think we could cook up next?